Yes.
Sounds good.
All right, so welcome everyone for the last TCS Plus of the semester. It's a pleasure to have Aaron Roth from UPenn who will be giving the talk. So before we do that, well, let me mention, so Thomas Hollenstein is operating today, and behind the scenes we're helped as always by Oded Regev, Anindya De, Gautam Kamat, and Clément Canon. So maybe, Thomas, you can go and present the groups who are joining us today.
Yes. So we have a group from University of Waterloo joining us today, led by Csalach Upadhyay. Difficult name, sorry about that. We have a group from Paris by Lila Fontes, Université de Paris 7. We have a group from Caltech led by Piyush Srivastava. Hello, Piyush. Then we have a group in PSU, which unfortunately still has some technical problems. So hi there. Now you're muted. So we have a group from NYU, led by Shravas Rao. Hey. And yeah, that's it. So back to you, Thomas.
Great. Thanks, Thomas. Well, it's a pleasure to have Aaron Roth give the talk today. So Aaron got his PhD from Carnegie Mellon 2010, advised by Avram Blum. After that, he was a postdoc at MSR, I think, and now he's a professor at the University of Pennsylvania. So Aaron has done a lot of work in the, algorithmic game theory, data privacy, differential privacy. He co-wrote a book with Cynthia Dwork on differential privacy. I don't know if Aaron is a co-founder of differential privacy or.
No, I'm not.
We can't say that. Okay, so
younger than that.
Okay, too young. Okay, you still wrote the book, but okay, all right. And so today he's going to tell us about some nice recent work that's also going to be at Stock in just a couple days on preventing false discovery in adaptive data analysis. I also wanted to mention, you should really not be afraid of asking questions. Just unmute yourself before you ask a question. We have in the audience not only the speaker, but also one of Aaron's co-authors, Vitaly Feldman, is here. So between the two of them, they should be able to answer any question that you want to ask.
Yeah, direct all of your questions at Vitaly. And if you feel the talk is too long, Vitaly is going to be giving a shorter version next week at Stock.
All right. Okay, although we do hope that you hang out for Aaron's talk today.
I'll hang out for the whole time. So hi everybody. And I guess if you're watching on YouTube, you'll just have to Snapchat me your questions. So this is joint work with a bunch of people who are pictured here. Most of them are not animations except for mine, and Vitaly's on the phone. And let me just start, introducing the problem of false discovery by talking about sort of a common email scam that you might have heard of before. Okay, so suppose, here I am sitting at Penn, and I get an email that offers me a great stock tip. It says, the Shake Shack is going to go up tomorrow. I should really invest in Shake Shack. All right, so I get this email. And it's not formatted in a particularly believable way. No reason I should trust this. But I read the email, and I see, lo and behold, the next day, Shake Shack stock, it actually goes up. All right, 50-50 chance the guy was right. I'm not too impressed yet. And then tomorrow, I get another email from the same guy, again offering free advice, saying, today I should short Shake Shack because it's going to go down. Okay, and to my surprise, it does indeed. The guy's right again, but okay, 25% chance he was right both times. And this continues. On the third day, he tells me it's going to go down, and sure enough, he's right. On the fourth day, he tells me it's going to go up, and lo and behold, it does. And suppose this continues for 10 days, and every day his prediction turns out to be exactly right. Okay. Now on the 10th day, he sends me an email. He says, "Look, I've been giving you all of this great advice. I've sort of proven to you that I'm pretty good at predicting stocks. 10 days in a row, I was right. I don't want to do this for free anymore. Just give me control of your finances and I'll invest them for you. I'm obviously very good at doing that, and I'll just take a small cut. Okay. So I get these emails, and how should I think about them? How should I think about whether this guy really is as good at predicting stocks as he seems to be? Well, I can try to sort of take a scientific approach and say, well, there's a null hypothesis that I want to see whether the data justifies me rejecting this null hypothesis. Okay, so maybe my null hypothesis is, this guy is just flipping a coin every day. He doesn't know anything about stocks. Okay, in which case, the chance that he was right 10 times in a row is pretty small. It's 1/2 to the 10th. So this is the chance that this data was generated in a world in which the null hypothesis was true. Okay, so if I, take sort of a scientific worldview, that's me in the corner there. I notice that the p-value, a p-value is just this number. What's the probability of seeing the observed data given the null hypothesis? P-value is pretty small. It's less than 0.05, which is the standard sort of test for significance. And so I think to myself, okay, I can safely reject the null hypothesis given this data that all of these predictions were just luck. This guy probably is really good at predicting stocks. I give him all my money. Okay, and I lose it all. So what went wrong in this analysis? Well, let's take a step back maybe and see what was happening. Okay, and the way this scam works is I wasn't the only one receiving these emails. Okay, the spammer here on the left sends out, say, 100,000 emails on day 1. And in half of them he predicts the stock's going to go up, and the other half he predicts the stock's going to go down. Okay, and he's right on exactly half of the emails he sent out. Okay, so on day 2, he sees what happens, and he focuses his attention only on the 50,000 victims for whom his first email was correct. Okay, and then he sees what happens on day 2, and again he continues only on that subset of people for whom his prediction was correct. And so, no matter what, with probability 1, there are about 100 people left after 10 days that have received perfect predictions for all 10 of those days and can do the calculation I did. Okay, so my error when sort of computing a p-value here, but when trying to figure out whether it was plausible that these observations came sort of just by chance, was my failure to take into account the size of the email pool, the size of the hypothesis pool. Okay, so indeed, it would have been extremely unlikely that he would be correct 10 times in a row if I was the only one receiving these emails, but I didn't take into account that there were sort of 100,000 trials, and it's not so surprising that 1 out of 100,000 trials was correct every time. Okay, so this is sort of the heart of what's a big problem in sort of empirical science, which is false discovery. And so here's a picture from an issue of The Economist recently called "Trouble at the Lab." And if you've been reading sort of the popular science literature recently, you might have seen a few times this claim that there's sort of a crisis in empirical science. Lots of science is not reproducible, and a big part of that is the multiple hypothesis testing problem, which is what we just saw a cartoon example of. Okay, so if I've got some finding with p-value less than 0.05, what that means is that it's got only a 5% chance of being realized by chance. But of course, we expect 5 such findings to have p-values less than 0.05, even if all of our hypotheses are wrong if we test 100 of them. Okay, and so this isn't like a new observation. This is well known, the multiple hypothesis testing problem. And it's not too hard to account for these if we know exactly how many hypotheses there are. Okay, and there's a large literature on what's called preventing false discovery in statistics. One of the sort of most powerful results is this sort of technique for controlling what's called the false discovery rate, the fraction of hypotheses that we sort of feel are true discoveries that in fact are false discoveries. And there's lots of tools for doing this. False discovery is sort of what empirical scientists call what a machine learning person would call overfitting the data. Okay, so there's lots of tools to prevent overfitting, cross-validation, using holdout sets. But a big problem is that a lot of the theory here focuses on non-adaptive data analysis, when in fact the practice of science is adaptive. So let me explain what I mean by that. Okay, so here's sort of the workflow of non-adaptive data analysis. Here's the data analyst on the left. Okay, so first you have to specify exactly your experimental setup and what hypotheses you're planning on testing. Then you go out and collect your data after you fix the hypotheses. You run your experiment, you test your hypotheses, you observe the outcome, and that's it. Sort of the crucial thing here is, after I test some hypothesis, after I look at the data in any way, I'm not allowed to now formulate a new hypothesis and go back and test it on the same data. Okay? So this is sort of in contrast to adaptive data analysis. After I observe the outcome, what I want to do, now I've learned something about the world, I want to revise my experiment, try a new hypothesis, go back and test it. Okay, and this happens all the time, not just sort of within, say, a single experiment, but like we share data. It's considered sort of, if you're a good scientific citizen, if I email you and ask you for the data set you used in your study, you're supposed to provide the data. We want science to be reproducible. But of course, if I read your paper, learn something about the world, and then want to run my own experiment on your data, we're no longer in the non-adaptive setting. Now the hypotheses that I'm testing are somehow informed by the data itself. And unfortunately, sort of all of the theory for controlling things like false discovery rate breaks. Okay, so let's sort of think about why adaptivity is troublesome. And I think we can view it sort of through the lens of the multiple hypothesis testing problem, the fact that there were 100,000 people who received that scam email on day one. Okay, so the problem is that adaptivity just sort of exponentially increases the number of hypotheses that we have to account for, because not only do we have to account for all of the hypotheses that we actually tested, but all of those that might have been tested. And let me just sort of remark that I'm, of course, being quite informal here, but in a few slides we'll write down a formal model. Okay, so you can view an adaptive data analyst as a decision tree, okay, where each node of the tree is some hypothesis I want to test, some question I want to ask about the data. And then the node branches as a function of what answer I get back. Okay, so I ask some question about the data, and then I learn what its answer is, and then as a function of the answer, I formulate a new question to ask about the data. Okay, so if you think about, sort of as a sort of function of what the answers might be to all of my questions, the trajectories I take down the tree are sort of the sets of all questions I might ask as a function of the answers I get back. Okay, so I ask question 1, I get the answer back. I ask question 2, etc. I take some path down this tree. The tree's depth k, so in the end I ended up asking k questions about the data. But the problem is, if the data were different, I would have asked different questions. So when I'm sort of accounting for the multiple hypothesis testing problem, it's not enough to account just for the k questions I actually asked about the data, but I sort of have to account for the 2 to the k questions I could have asked about the data, given the answers I might have gotten. Okay, so let's think about this problem, and now let me sort of write down a formal model. And let me just sort of point out at this point that this is one possible formalization of the problem. What I'm going to talk about is actually not the only one we can say things about. So this is going to be a special case of sort of the contents of the papers I'm talking about. We can say things more generally than just asking the kinds of sort of simple numeric valued queries I'm going to talk about here, but let me write down a simple model for concreteness for the talk. Okay, so I want to talk about what are called statistical queries, which you might be familiar with if you've studied sort of pack learning. So in this model, we've got some data universe. This is sort of the space in which data elements might live. Okay, so it's not important what it is, but for concreteness, let's say it's the d-dimensional hypercube. Okay, so every sort of entry in your data set is just some element that's got d Boolean features. Okay? And the main object of interest is there's some distribution over this data universe. This is sort of the distribution from which data is going to be drawn. This represents the real world. Basically, we want to learn facts about this distribution. Okay, but the problem is we don't have access to the distribution that sort of governs how the world works. All we have access to are samples from that distribution. Okay, so we've got some finite data set which consists of n points sampled from this distribution. Again, this is the only access we have to the distribution. What we're going to be interested in are sort of answering questions about the distribution via the data set, and the concern is going to be overfitting the data set. So a statistical query is just defined as some predicate over the data universe. Okay, so it's a predicate that you plug in some data element, any data element, into this predicate, and it spits out some number between 0 and 1. And the answer to the statistical query, sort of the real answer, the one we want to estimate using our data, is just the expected value of this predicate if I were to evaluate it on a random universe element drawn from this distribution. Okay. And what we want to implement is a statistical query oracle, which is just some algorithm for answering statistical queries. So, some algorithm, we'd plug in a query, right? So the domain of this function might look confusing. It's just the, set of all possible predicates. And so we give it a query, and we expect to get out of it an answer to that query, a number between 0 and 1, which is supposed to represent the expected value of this predicate over the distribution. Okay, and we're interested in the accuracy to which we can answer these queries. So we'll say that a statistical query oracle has accuracy tau on some collection of statistical queries if for every query in our collection, the error when I compare the answer I get from my oracle compared to the real answer is at most tau. Okay, so this is some algorithm. I give it a query. It's supposed to estimate for me the value of this query on the distribution. And what I care about is sort of the worst case over all of the queries I might ask of sort of the error, how wrong it is compared to the true answer, the true value of this query evaluated on the distribution. Okay, does that make sense? Yeah, I don't have a lot of feedback on here, but if you guys sort of nod, I'll feel confident going on. Any nod? A little bit of nodding. Okay. So where do these oracles come from? We don't have access to this distribution, so the only way that these oracles can have any idea at all about what the right answer to these queries are is via the data set. Okay, so we have to build an oracle from data. Okay, so the oracle is actually parameterized by the data set. And the main quantity of interest is what's called in sort of the learning literature sample complexity. So if I want to answer a set of k queries up to some accuracy tau, how much data do I need before I can get a statistical query oracle with the property that I want? Okay, so let's think about this. Okay, so the first observation, and this is sort of an easy exercise, is that if the queries are chosen non-adaptively, then I don't need much data. Okay, so let's consider what I'm going to call the naive mechanism here, but this is essentially, the only mechanism anyone ever uses. Okay, so the naive mechanism, right? You've got your data set. I give you some predicate phi, and I want you to tell me what is the expected value of this predicate on the distribution from which this data set was drawn. Well, what are you going to do? You're going to compute the sort of empirical estimate of that quantity. That's what the naive mechanism does. It just evaluates, well, what's the average value of the predicate over the elements in the data set, right? And this is an unbiased estimator because the query is independent of the data. If the queries are chosen non-adaptively, okay, so you just give back the empirical estimate of the query on the data set that defines the naive mechanism. And sort of an immediate theorem is that I can get a tau-accurate answers to any set of k non-adaptively chosen queries. And the size of the data I need, the size of the data set I need is only logarithmic in the number of queries I want to ask, so log k over tau squared. Okay, and this is immediate, basically by a Chernoff bound and a union bound. Okay, I need roughly sort of, right, because each of the entries in this data set is drawn independently, so I need roughly 1/tau squared samples to estimate a single statistical query up to accuracy tau on the distribution. And I need to take a union bound over k queries, but I've got pretty good concentration since these are independent, so I can take only log k over tau squared samples. Okay. But the bound that the naive mechanism gives us for adaptively chosen queries is exponentially worse. Okay, so it's going to say if I'm going to choose k queries adaptively, right, where I choose the next query as a function of the last query, my sample complexity is no longer log k over tau squared, it's more like k over tau squared. So it's exponentially worse. Again, it's not hard to prove this bound. We're just going to sort of, again, use a turn-off bound and a union bound, but this time not only over the k queries I asked, but over all of the queries I might have asked in the sort of decision tree. Okay, so each query has at most n possible answers. The branching factor of the decision tree is at most n. So there's n to the k queries we might ever ask, and so we need to pay log of that, k log n. Okay, and this is not just it turns out this isn't just a sort of, loose analysis. This bound's almost tight, meaning if you're going to use the naive mechanism, if you're going to answer queries exactly with their empirical estimates on your data set, then it's not hard to use an exercise. You can do it at home. It's not hard to figure out a set of queries you could ask that's going to force the naive mechanism to give you an inaccurate answer if the data is much smaller than this. Okay, so this is sort of annoying, right? Like this bound says if we're going to use the naive mechanism, at least what we're going to expect to get, sort of the sample complexity we need to answer k queries is going to get exponentially worse if our queries are adaptively chosen. Okay, now this is about this is tight for the naive mechanism, but the question we want to ask is, using some other mechanism, some other way of answering these queries, is there some way in which we can answer adaptively chosen queries and get the sample complexity back down to log k? Okay. So that's the question we want to ask. So, let me now introduce sort of one of the main characters in this talk, differential privacy. So if you haven't seen it before, here it is. So differential privacy is a property of an algorithm. Okay, so in particular, it's a property of a randomized algorithm that takes as input a data set. Okay, a data set is just a collection of n records from whatever your data domain is. And it's a randomized algorithm, so it takes as input this data set, and as a function of the data set, it induces some probability distribution over its outcome space. And if the algorithm is differentially private, what that means is that if I now look at the distribution induced over outputs when I use this data set, and I look over the distribution induced over outputs when I change one element in the data set, these two distributions have to be very close. Okay? So formally, I've got my data universe, and the data set is just some subset of elements in the data universe, and two data sets are neighbors if they differ in only one data record, if I can get from one to the other by adding or removing just a single data element. Okay? Then an algorithm, M, is said to be epsilon delta differentially private if no matter what pair of neighboring data sets I have, and no matter what output of the algorithm X I look at, when I compute what's the probability that my algorithm outputs X when its input is D, this should be within a 1 plus epsilon multiplicative factor and a delta additive factor of the probability of the same output being realized when instead of running it on D, I run it on D prime. Okay, so differential privacy is some kind of Lipschitz constraint that says the algorithm has to behave in a very similar way when I add or remove any single element from the data set. And similar way means I can't change the probability of any event multiplicatively by more than 1 plus epsilon and additively by more than delta. That's differential privacy.
Sorry, Aaron, can you say just a little bit more about this? Why this particular choice of measuring the error? Why not just measure the statistical distance between the distributions?
Good. Yeah, that's a great question, and the answer depends on the application. But so typically, as you can tell from the name, this is generally used as a sort of measure of privacy, something that you hope is going to capture like intuitively what your notion of privacy is. Okay, so so say we were going to use statistical distance instead. So suppose we said sort of two algorithms were epsilon close if they're an algorithm was epsilon private if when I plug in database D versus D prime, the statistical distance between the two was only epsilon. Well, one thing that I could do that would satisfy that definition is I could sample an epsilon fraction of the people in the data set and just publish that subset of the data. That would induce only epsilon statistical distance between two data sets. But we
Well, Aaron, we lost. I don't know if it's me, but I lost your sound.
No, we can't hear you. The sound is somehow gone. Yeah.
Yes.
Okay, can you hear us?
Yeah, so he's noticed. So this happened last time, right? So maybe you just need to quit and rejoin. That's what fixed it last time.
What did it last time? Though last time it was different, but what did it was that the speaker quit and rejoined. But yeah, I guess let's try that.
All right, sorry about that, everyone. This will be fixed quicker than it took us last time because the speaker is aware of the problem, so he'll just join back.
Welcome back, Aaron.
So I think we're not hearing you. I don't know if you're talking. One thing to check is the settings at the top of the Google window.
So here, this Cogito, I hate doing this.
We have your slides.
We have your slides, yes.
But we have no sound coming from you. Maybe if I mute. Oh, okay, that was stupid. I muted you, so you shouldn't mute yourself, right?
You can unmute people now. I unmuted him, but it doesn't seem to help. We still cannot hear you.
So did you check the settings that it's pointing to the correct mic? Yep.
Can you hear me now?
Yes.
Okay, using a different microphone now.
Okay, so that's better than no microphone. The audio quality is slightly worse, but.
Okay. Well, I'll try to talk louder. Anyways, the point of a multiplicative difference is that you're constraining that even extremely low probability events can't substantially increase in probability. And so for privacy, the thought is that low probability events can still be disclosive. Also for the application, we're going to get here, statistical distance wouldn't be strong enough.
So you're trying to prevent this, but still up to some delta, right? So you don't want.
Yeah. So normally we think of, for privacy, normally you'd think of delta as being like really a tiny thing, like exponentially small in n, if possible.
Okay, thanks.
All right. So why should differential privacy be useful here? And the intuition is that differential privacy is a stability guarantee. In particular, it says changing one data point can't change the outcome very much. And what we're trying to do is prevent overfitting. And stability is going to imply generalization. It's going to imply this fact that things we say about the data set should also be true about the data set from which, should also be true about the distribution from which the data set was drawn, because somehow overfitting is not a stable operation. Okay, if I start resample, if I start sort of one by one resampling points in the data set from the distribution from which the points were originally drawn, if you've overfit to the data set, if you've learned something that's true about the data set but is not true about the distribution, then as I start doing this, your hypothesis is going to have to change substantially, because the thing that you had thought was true about the original data set is going to start not being true anymore. On the other hand, if you haven't overfit, if the thing you learned was true about the underlying distribution, as you start sampling new points, you don't have to change much. Okay, so that's sort of the intuition for why overfitting isn't a stable operation. Okay, so let me now state sort of the formal connection that we prove. Okay, so the connection is this. Suppose I've got some algorithm for answering queries, okay, some statistical query oracle, that satisfies two things. Okay, so first, the algorithm is differentially private. In particular, it satisfies epsilon delta differential privacy, where epsilon is tau, the accuracy parameter I want, and delta is, for this theorem, something pretty tiny, something sort of exponentially small in 1 over tau. Okay, so that's property 1, that the algorithm is differentially private. And property 2 is that the algorithm, given any set of k adaptively chosen queries, can answer these queries up to error only tau with respect to the data set. Okay, not with respect to the distribution, that's what we want to get, but with respect to the data set. Okay, so the two properties I want are that 1, the algorithm is differentially private, and 2, the answers it gives me are always close to the empirical estimates of the queries on the data set itself. Okay, so the naive mechanism satisfies property 2, where tau is 0. It's always giving me exactly the answer on the data set. I'm willing to relax that a bit. I only need approximately the answer on the data set, but in exchange for that, I want also that the algorithm should be differentially private. Okay, so if I've got these two properties, then so long as my data set is even a little bit large, you know, just sort of the size you'd need to answer k queries non-adaptively, then my algorithm is actually tau accurate on any set of k adaptively chosen queries, where now when I say it's tau accurate, I mean it really gives the right answer on the underlying distribution itself. Okay, so the theorem here is that if you're accurate with respect to the data set and you're differentially private, then you also have to be accurate with respect to the distribution from which the data was drawn. Okay? And now let me note that this was the theorem we have in our upcoming stock paper, but you know, science moves quickly. So there have been 2 papers, in fact, improving on this. The theorem I'm quoting here is an improvement due to Nissim and Stemmer. And there's a similar theorem by Vasily, Smith, Steinke, and Ullman that significantly improves the parameters. So in our theorem, we need delta, the delta parameter, and the privacy guarantee to be really small. We need it to be exponentially small in the accuracy parameter we have, e to the minus 1 over tau. But it turns out the theorem's still true even if the delta parameter is also set to tau. Okay, this is an improvement due to the 2 papers here. I've got links to both of them at the end of the talk. So what this means is that it sort of reduces the problem to trying to find differentially private algorithms which are accurate on the data set. And unfortunately, that's what we've been in the differential privacy community studying for the last, like 10 years. So we've got a bunch of those. Okay, so this theorem, it's not super hard to prove, but I don't know a great way to build a lot of intuition for it in a talk. So what I'm going to talk about instead is a slightly weaker and easier theorem. Okay, so here's a theorem that we can prove in the talk. Okay, so this is similar, but it's saying, suppose we've got a mechanism that answers queries. Condition 2 is the same. Okay, it promises that for every query you give me, I'm going to spit back to you an answer which has error at most tau with respect to the empirical estimate of the query. Okay, but condition number 1 is different. Now it says, rather than insisting the algorithm be differentially private, I'm going to insist that it has an output that can be described concisely. So the set of answers that it gives should be describable with at most t bits. Okay.
Aaron, there was a question by someone who doesn't have sound, but I'm not sure I understand the question. This is Ref. He's asking if you can get similar guarantees for delta equals 0.
Yes. So there's also a theorem you can get where delta is equal to 0. I mean, so I don't quite know what you mean. So these parameters here, like I'm now stating your theorem, of course, but all we need is that the algorithm be like epsilon delta differentially private for epsilon like less than or equal to tau and delta less than or equal to tau. So like in particular, if delta is 0, okay, you're right. It's a separate theorem, but there's a theorem with weaker guarantees for delta equal to 0. Okay. But I'm not going to talk about it. The guarantees are somewhat weaker when delta equals 0. In fact, the guarantees you get when delta are equal to 0 are basically going to be the same as the guarantees we get in this easier theorem. Okay, so in this easier theorem, rather than requiring that the algorithm be differentially private, I'm just going to require that the algorithm's output have short description length. It should be describable with only t bits. Okay, and anything I know how to get with epsilon 0 differential privacy, I know how to get with this theorem as well. But with the stronger theorem, with epsilon delta differential privacy, we get results that I don't know how to get with this description length theorem. Okay, but the punchline is if your algorithm has short description length and it answers things accurately on the data set, then so long as your data set is larger than t plus log k over tau squared, then the answers it gives you will be tau accurate with respect to the underlying distribution as well. Okay, so that's the statement of the easier theorem. Yeah. And it's not hard. Oh, is there a question?
Yes. Just to make sure I understand, do you think of the input of A's input as being D instead of samples?
So I think of A as being sort of parameterized by D. So fixing a database, you now fix this algorithm which can take in queries and give you answers.
I guess my question is the differential privacy with respect to what? To the
with respect to D. It's got to be differentially private with respect to D.
So in that case, why isn't the naive mechanism kind of private? Like if you add maybe a bit of noise,
if you added noise, you'd be able to make it private, yeah. So there are better things you can do than just adding noise, but that's one of the simple things you can do.
Okay. Thanks.
Yes. Okay. So, it's not hard to show this theorem. Remember again that I can view the data analyst as sort of being a decision tree where I've got, at level 1, the query I'm going to ask first. At level 2, all of the queries I might ask as a function of the answers to the first query, et cetera, et cetera. It's depth k, so, there could be exponentially in k many queries I might ask. But if the outcome of the, if the set of answers given to me by the statistical query oracle can always be described by only t bits, then no matter what the data set is, no matter what questions I ask, there's only sort of 2 to the t different sets of distinct outputs it can give me. And since the trajectory of queries I end up asking adaptively is fixed once I fix the outcome of the queries I've asked of this algorithm A, that means there's only 2 to the t different trajectories I could actually take through this decision tree. And I don't have to ask for uniform convergence over all possibly 2 to the k queries. I only need to ask for uniform convergence over the queries that I might ever actually ask while interacting with this mechanism. There's 2 to the t different trajectories I might take down the tree. Each one has only k queries. So I only need to sort of union bound over k times 2 to the t queries. And the sample complexity I need, therefore, is log of this. So it's t plus log k. Okay, so that's that theorem. It's not hard. So, nevertheless, right, that theorem gives you a reduction from, a reduction to the problem we want to solve. But to use the reduction, we need to figure out a way to answer lots of adaptively chosen queries in a way that has only short description length. Okay, so it reduces the problem to answering this possibly simpler problem. Can we answer lots of queries such that the answers have short description length? And the answer is yes. This isn't the best way you can do it, but this is a very simple way based on a paper I had with Tim Roughgarden in 2010. Except there we added some noise for privacy. But to analyze this, you only need to realize a very simple fact. Okay? For any set of k queries, there's always a data set of size only log k over tau squared, such that the empirical estimate of all of the queries, all of the k queries on this data set, differs by the real answer from the real answers by only tau. Again, this is this follows from a turnoff bound and a union bound, the fact that for any fixed set of k queries, if I viewed them as being non-adaptively chosen, a random sample from the distribution would answer them all correctly. Okay, so for any set of k queries, there exists some data set that's pretty small that encodes all of the correct answers, and the set of all such data sets is merely exponential in the size. So the set of all such data sets that are of size log k over tau squared is only 2 to the d, that's the number of distinct points there are, times log k over tau squared. Okay, so let's think about how we might answer queries. So I'm gonna start by writing down, the set of all possible data sets of size log k over tau squared. Okay, so I'm gonna call that set C1. And now you're gonna start asking me queries. And I'm gonna attempt to answer them by doing the following. Okay, I'm gonna take your query, and I'm gonna look at the set of data sets I've got in my current set CI. I'm gonna evaluate the answer to your query on all of them, and I'm gonna take the median answer. Okay, and now I'm gonna look, is that median answer evaluated on all of the data sets that are consistent with the queries you've asked so far? Is that median answer compared to the real answer, if I were to evaluate it on the data set, does that median answer have error more than tau or not? And if it doesn't have error more than tau, I'm not going to tell you the answer to your query on the data set. Instead, I'm just going to tell you the median answer of the query you asked on all of the data sets in set CI. Okay? And I won't change the set CI. CI plus 1 will just be the same as it was before, CI. Okay? On the other hand, if this answer I was trying to give you, the median answer of this query on all of the consistent data sets so far, has error more than tau, I can't give it to you then, because I'm constrained to giving you answers that have error at most tau. So in this case, I'm going to give you the real answer. I'm going to give you just the answer to your query evaluated on the data set, and I'll round it to the nearest multiple of tau. And then I'll update the set of data sets I've got to be the set. I'll eliminate any data set that isn't consistent with the query you just asked. Okay, so now my set CI plus 1 will consist of all of the data sets that were in set CI that had the right answer on the query you just asked. Any data set that had a different answer, I throw it away. Okay? And I want to say if I have to give you the answer on the data set, if I have to give you the real answer to the query, I'll call that query a hard query. But otherwise, I'll call the query an easy query. Okay? And easy queries are those that I was able to answer for you without having to tell you the real answer on the data set. I was able to answer them for you just by looking at CI. So let's make a couple observations. Okay, the first is that the answers I give you are, by definition, tau accurate, because I'm either giving you exactly the real answer, which is perfectly accurate, or I'm giving you an answer that, by definition, has error at most tau. Okay? The other observation is that there can be, at most, log of C1 many hard queries, right? Because if I've got a hard query, what that means is that the median answer on the data sets in CI differed from the real answer by more than tau. In particular, that means, since I was trying to answer with the median, at least half of the data sets in CI differed from the real answer by more than tau. And so when I updated my set of consistent queries to construct my set of consistent databases to construct set CI plus 1, I removed half of them. So every time I've got a hard query, I get to divide the size of the set CI in half. And I know the size never goes below 1, because there's one data set in there that's consistent for any set of k queries I ask. So every time I have a hard query, I cut the set in half, it never goes below 1. I know the number of hard queries I can never ask isn't more than log of the size the set started with, which is only d times log k over tau squared. Okay? So now so what this means is that no matter what set of queries you ask, I can always describe to you the entire interaction, in particular all of the answers to all of the k queries you asked, by telling you only d times log k over tau squared times log k plus log 1 over tau bits. So let me tell you where this comes from. Okay? So the first term here, d times log k over tau squared, is the number of hard queries that might ever occur while you're interacting with the statistical query oracle. Okay? Now, if I want to communicate to you what trajectory the data analyst took down this tree, the observation is the only thing I need to tell you are the depth of the hard queries and their answers. Okay, the claim is to specify a trajectory down the tree. I just have to tell you for each hard query what was its depth, what was the index of each hard query, and what was its answer. Because once you know what the hard queries were and what the answers were, that fully specifies what these sets Ci are. Okay? And so you know for any query that was an easy query what answer I would have given you. You can compute that just from the Ci, and therefore what the next path down, what the next sort of step down the tree would be. Okay? So for each of the hard queries, for each of the d times log k over tau squared queries, I have to tell you only log k bits to tell you the depth of that query, and the answer up to tau bits of up to precision tau, which takes only log 1 over tau bits. Okay, so not too hard. And just plugging this into our theorem, plugging this into the easy theorem, what you get is that there's an algorithm that can answer k adaptively chosen queries now, while guaranteeing tau accuracy and needing sample complexity only d times log squared k over tau to the 4th. Okay, so note that already this is a, at least if k is big enough, this is a big improvement over the naive mechanism. Right? The naive mechanism had a linear dependency on k, and here we only have a polylogarithmic dependency on k. Now in exchange for this, we've got a dependency on the dimension, which we didn't have before, and we've got a worse dependency on tau. But at least the dependency on k is only polylogarithmic. Okay? So that was the easy theorem. Well, what do we get with the real theorem? Well, this is the theorem actually due to Basili et al. And also due to Nissim and Stemmer. So this is the theorem I showed you with the improved parameter, where you don't have to set delta to be tiny, you only have to set delta to be tau. And using a state-of-the-art private mechanism for answering queries due to Hart and Rothblum. Right? So comparing to the easy theorem, the dependency on d is improved to square root of d. The dependency on k is now optimal. It's now log k. This is exactly the dependency you had for non-adaptively chosen queries. And the dependency on tau is now no longer tau to the 4th, but tau cubed. So you might hope to improve this to tau squared, which is what you want, which is what you get in the non-adaptive case, but substantially better. This is substantially better than the naive mechanism. So one caveat, this is an information theoretic result, the algorithm which realizes this bound actually has running time 2 to the d per query. Okay? But another result we have is a different algorithm. It doesn't have quite as an impressive a bound. It doesn't give you sort of this log k dependence. But it's simple, efficient, and I dare say practical. Okay, so let me just briefly describe for you, using these techniques, an efficient method by which you might reuse a holdout set with essentially no extra running time. Okay, so first of all, what's a holdout set? So this is sort of a diagram of some data analysis procedure you might try. Okay, so you've got your data analyst who has partitioned her data into a training set and a holdout set. She's got unrestricted access to the training set. She, say, learns some classifier. She does all sorts of, adaptive things possibly. But the important thing is she hasn't touched the holdout set. And now she wants to verify something like, the classification error of her classifier. And so she validates her classifier by checking, say, its empirical classification error on the holdout set. And If she uses it only once, this is a sort of rigorous thing to do because the holdout data is selected independently of the classifier. But again, for the same reasons we've discussed before, the holdout set can only be used once. You can't see the answer on the holdout set, train a different classifier on the training set, and then go back to the holdout set, because now you run the risk of actually overfitting the holdout set as well. Okay, so using a different technique from differential privacy, we propose the following workflow. You still have unrestricted access to the training set, but now we give you access to the holdout set only through a very simple differentially private mechanism. This one's efficient. And the result is you can use the holdout set to validate your hypothesis many times. Okay, so how many times? The theorem is going to be that our algorithm, which we call Thresholdout, which makes more sense once you know what the algorithm is, but I don't have time to describe it for you, gives you tau accurate estimates for any sequence of adaptively chosen queries until you've asked roughly n squared queries that happen to overfit the training set. Okay. What it means that a query overfits the training set is that you've asked some query such that when I evaluate the answer to the query on the training set compared to on the test set, the answers actually differ by more than tau. Okay, so what this does is you can use the holdout set as you normally would, except now instead of using it just once, you can use it a large number of times. And how many times you can use it depends on how many times you actually overfit the data. So if you're a really good data analyst and you rarely overfit the data, you can use it repeatedly, essentially an unbounded number of times. Every time you ask some query which happens to have overfit the data, you use up part of your budget, and you've got essentially n squared chances to ask queries and overfit before we have to cut you off. Okay, compare this to sort of the naive mechanism, which if you want rigorous guarantees, really only lets you ask one query, validate one query on the holdout set. Okay, and this actually works pretty well. So here's sort of an experiment we run. This is all synthetic data, but it's sort of to illustrate a point. You can generate a data set that's got, say, n is 10,000. So we've got 20,000 data points, and they're going to be split evenly between a training set and a test set. And we've got 10,000 binary attributes. And what we're going to do is we're going to try to, one by one, find variables which are correlated with the label. Okay? And we're going to validate those. So if we find a variable that appears to be correlated with the data on the training set, we'll test and see whether it's correlated with the data on the holdout set. And if it is, we'll add it to the set of variables we're selecting. We're going to try to select the k variables that are most correlated. And then on top of that, we'll learn a linear predictor. We'll do like linear regression on those k variables. So this has one round of adaptivity. First, we select the variables, and then as a function of those variables, we learn a linear classifier. Okay, and we'd like to find what's the best value of k. Okay, and so we run two experiments. In the first case, there's actually no correlation at all between the data and the labels. Okay, so as a function of the number of variables we select, that's the x-axis. And on the left, we're using the standard naive holdout method, and on the right, we're using ours. You can track the error or the empirical accuracy of our classifier, the one we learn, on the training data, on the holdout data, and on a freshly drawn data set. Okay, so the point is here, there's no correlation between data and labels. So you can't do better than 50-50 guessing on a fresh data set. That's why the red line is always at 50%. But when you use a standard holdout, you can see with the blue line, not only do you overfit the training set, you overfit the holdout set as well. And so you've basically broken the holdout set. It looks to you like you've learned a good classifier, but you haven't. When you use Thresholdout, the overfitting doesn't happen. You still overfit the training set, but you can see via the green line you don't overfit the holdout set. Okay, so it correctly sort of corrects for overfitting. On the other hand, you want to be able to actually learn when there is some correlation. So in the second experiment, 20 of the attributes actually are highly correlated with the target. The remaining attributes are uncorrelated. And now, when you're using the standard holdout method, of course you continue to overfit, as you select more variables on the training set. But you also overfit on the holdout set, and if you're trying to select the sort of correct number of variables, it looks like the best point is selecting 500 variables, which is wrong. On the other hand, with Thresholdout, the fit to the holdout set, the green line, tracks very closely the fit to the sort of the true error, the error on a new draw from the distribution. In particular, it selects the correct number of variables. Okay, so it's a sort of a empirical question.
Yeah, I didn't get. Why is why are the blue curves different? What's happening there? Aren't you doing the same thing with the training data? So is that a result of the different kind of feedback you get from when you test?
Yeah, so the feedback is, so things aren't exactly the same. You are getting different feedback when you test, so you might be selecting different subsets of variables.
But why would threshold, is there any reason why would the threshold out thing would be better?
You're getting, it's only spuriously better. I mean, it's better training accuracy, but that sort of means increased amount of overfitting on the training data.
Okay, so that's bad. Okay, I see.
So in that sense, it's bad. Yeah, I'm not sure why they're different, but certainly the variables that are being selected are different when you're getting different feedback from the holdout set. Also, the data sets are generated randomly.
Okay.
Okay. So there's lots of future directions, I think, both in theory and in practice. So in theory, I think we don't fully understand adaptivity in data analysis. So, is it possible to obtain improved bounds? Ideally, you'd like to get sample complexity for adaptively chosen queries that are just as good as for non-adaptively chosen. So you'd like to get sample complexity like log k over tau squared. And we sort of have hit the limits of the kinds of bounds you can get via differential privacy, because we know that it's not possible generically to improve these generic transfer theorems that say if an algorithm is both accurate on the data and private, then you get generalization. It's not possible to improve those theorems in a black box way. And we also know that the algorithms that we're plugging in, the private algorithms that answer queries accurately on the data set, are sort of optimal with respect to, they're the optimal differentially private algorithms for this task. So there's no better way to improve on these bounds, either by giving a better black box sort of transfer theorem via privacy, or by giving a better private algorithm. But that doesn't mean that there's not a better way to. That doesn't mean our bounds are tight and you can't improve on them via other methods. Okay, so as a fundamental question, we don't know whether differential privacy is the best way to achieve generalization, and if it's not, it would be useful to understand. This is an important quantity, so it would be useful to understand. Is there some information theoretic measure that characterizes generalization in adaptive data analysis? We've got a recent paper I'll point to on the next slide that gives a partial but not complete result to this. On the side of practice, this algorithm we've given for answering exponentially many queries, it's not practical. Now, that doesn't mean there aren't practical methods that use these techniques for real data analysis problems. Thresholdout is one of them, but there's more to data analysis than holdout sets. I think there's a lot of room for using techniques of this sort for various practical real problems, and of course in practice constants matter. Okay, so that's it. Just to point you to the various papers I've talked about. So the main theorem is from, and this is a paper that's going to appear in Stock next week. Vitaly will present it. It's called Preserving Statistical Validity in Adaptive Data Analysis, and it's on arXiv. There are two papers that improve the theorem, in fact. The corollaries I stated are with those improved bounds. One is by Vasily, Smith, Steinke, and Ullman. It's called More General Queries and Less Generalization Error in Adaptive Data Analysis. And there's an arXiv link. And the other is by Nassim and Stemmer, called On Generalization Properties of Differential Privacy. And the description length arguments and the more general measure I hinted at, as well as this algorithm Thresholdout and experiments, this is in a paper that we just posted on arXiv a couple days ago called Generalization in Adaptive Data Analysis and Holdout Reuse. And if you want to get into this literature and learn more about differential privacy generally, I recommend the book I've got with Cynthia, which you can download for free from my website. So that's it. Thanks.
Thanks. So we'll take questions. There's a question from Piyush in the chat. So Piyush is asking if you're still using hard queries in the implementation of the Thresholdout.
Yeah, so Thresholdout is a really simple algorithm, so you don't have to worry about hard queries. So basically the algorithm is just the following. You submit to the algorithm the query you want to validate on the holdout set, as well as the value that query takes on the training set. Okay, and the algorithm's going to add a little bit of noise to what the algorithm's going to do is it's going to try to compute the difference between the value of the query on the training set and the value of the query on the holdout set. And to make sure that's private, it's going to add a little bit of noise. And it's just going to compare that to a threshold, which is going to be something like tau, the error you want. And if the noisy error is above tau, it'll give you a noisy estimate of the real answer on the holdout set. And otherwise, it'll give you just the answer that the query evaluates to on the training set. So if you want, you can think about this, I guess, as a division of the queries into hard queries and easy queries. Here, it turns out that the easy queries are those queries that didn't overfit the holdout set. That's it.
Thanks.
Any other questions?
Questions in the audience?
If you're on YouTube, you can Snapchat them to me. All right. Haven't gotten any.
Okay. If there's no questions, I think we can thank Aaron for his talk. Thanks, Aaron. I guess everyone's clapping, but
can't hear them. But
so this was last talk of the semester. So it's been a nice semester. Thanks everyone for joining us every time. I hope you've been enjoying it. We're probably going to take a little break over the summer, and we'll be back in the fall. So let's keep in touch. Oh, there's a question. Whoops, sorry. Before we get off, Ref has a question. Sure. Do you want to ask it? You don't have sound, so go ahead. You type it, I guess. Aaron, you can see the chat, right?
Yes.
Okay.
Ready to answer the question. Permission to ask the question.
Yeah, maybe he's typing. I don't know. Yeah, I think he's typing probably.
What results you have for adaptive batch queries? So you mean you ask like some set of K queries, but not every query is adaptively chosen. Like you ask K1 queries, and then based on the answers to those, you ask another K2 queries. Yeah, so you can get results for this kind of thing as well. So I don't know how to, just for a sort of information theoretic bound, I don't know how to get a substantially better one. But you can get interesting results for efficient algorithms if your queries are, if you've got a lot of queries but are only coming up with them using a small number of rounds of adaptivity. Right, so what you can do is you can get, there's a theorem that you can get which lets you answer the sample complexity you need depends only logarithmically on K. It depends only logarithmically on the total number of queries you ask. But it also depends on the square root of R, where R is the number of rounds of adaptivity you have. Okay, so you can get sample complexity like log K square root of R, and the nice thing about this algorithm is it's efficient. So unlike the algorithm, which sort of always gets sample complexity log k no matter what, and that algorithm runs in time 2 to the d per query, this algorithm runs very efficiently. And it's very similar to the thresholdout algorithm. The point is, between rounds of adaptivity, you don't have to worry about overfitting. Right? Between rounds of adaptivity, I might as well use something like the naive mechanism. So the way the algorithm is going to work is I'm going to have a, some fixed, say training set. I'm just going to basically answer questions naively on the training set. But I'm going to use something like the thresholdout algorithm to determine when you've overfit. Okay, now whenever you've overfit, I'm going to just refresh your training set. I'm going to throw it away and get new data. But the point is, it's extremely unlikely that you overfit at any stage that's not between 2 rounds of adaptivity. And so sort of so you can get results that such that the sample complexity scales only with the number of rounds of adaptivity and still be efficient. Good question.
Just a quick correction. I think you might have mentioned that we get a square root dependence on the number of rounds.
Yeah, it's only linear, you're right.
Yeah, it's only linear. Okay.
Yeah, so Vitaly, I was wrong when I stated the bound. So even though it's true that we can detect sort of, R squared round sort of instances of overfitting, because what we have to do is refresh your training set every time you've overfit, the sample complexity is actually linear in the number of rounds of adaptivity. So the sample complexity is number of rounds of adaptivity times log k. Good question.
Okay, thanks. Any other questions? All right, thanks, Aaron.
Okay.
Thanks everyone for joining. I guess we'll get offline, but anyone who wants to hang out is welcome to stay hang out. We'll just take the live video down, maybe.
All right, thanks everybody.
Yes, thanks everybody, and see you next semester. Thank you.